Hey Phys One Kids, Campbell here. In our second video on circular motion, we're going to talk about vertical circles. You know, roller coasters, loop-de-loops, or spinning a bucket of water on a string because you would do that? Maybe. Maybe I'll do it in class. But for this video, I'm going to have to do some writing on the screen. So guess what? You're not going to be able to watch me. I'm getting rid of myself because I need to write neat this time. So let me change things up. All right, so the key to vertical circles is looking at the forces because the forces in a vertical circle are constantly changing because as it moves in a circle, right, if you think about it, the force of gravity is always straight down, but the force towards the center of the circle, our circular force, is changing as it moves in the circle. Now, there's one thing that's really important about vertical circles, because normally we think of down as negative, but when we deal with circles, the force and the acceleration that are towards the center of the circle are always going to be positive. So anytime we're working in a circle, anything that points towards the center of the circle is going to be positive. So if I'm down, if I'm up here and a force is pointing down, that's actually positive. And you'll see when we write our equations. So let's take a look at the bottom of a circle. So here I am swinging a ball on a rope. And so if I want to look at a free body diagram of this ball on this rope, right, we're going to have the force of gravity down. And remember, the equation for force of gravity is mass times the acceleration due to gravity. And we have our tension force up, the force of tension. So if I want to write an equation for the bottom of our circle, we get that the force of tension is towards the center, so that's our positive force, minus the force of gravity, and I'm going to write mg in for that force of gravity, so I don't have to do too much rearranging. That is equal to the mass times my centripetal acceleration, which, remember, centripetal acceleration is v squared over r. So if I rearrange this equation, we get that the force of tension is equal to our circular acceleration times mass, so our mv squared over r, plus the weight of the object. So at the bottom of the circle, I feel the maximum force. So if the string is going to break anywhere in a vertical circle, it's going to be at the bottom because that's when that tension force is going to be the greatest. This is also true if you're like in a roller coaster, right? If you're in a roller coaster, you're in a vertical circle and you get to the bottom of that loop-de-loop and you feel like you're being squished into the bottom of the car that you're in. So again, at the bottom of a vertical circle, the force, that tension force or the normal force, or whatever that force is that's pointing towards the center of the circle, is going to be at a maximum. Now let's move to the side. If I'm at the side of the circle, right now, while my force of gravity, right, is still straight down, it's not in any way affecting our center force or our force of tension, right? Anytime we have forces that are on separate axes, then they don't affect each other. So at the side of a circle, if I'm perfectly at the side, then my equation for the circular force is just the force of tension. So the force of tension is equal to mass times the centripetal acceleration, or mv squared over r. So here, your weight, or the weight of the object, has no effect on the tension. In this case, because we're talking about tension, but any sort of circular force. Now, what if we go a little bit higher? When I get here, right, the force of gravity is still pointing straight down, and my tension force still points towards the center of the circle. That's the thing keeping me in the circle. But now you can see that the weight has a component in towards the force of gravity. It's at some angle, we'll call theta. So if I'm at an angle to the side, in this case, when I'm above the center of the circle, I have the force of tension plus, because remember, towards the center of the circle is positive, some mg, your weight times the, let's see, if we were to make some sort of right triangle here, we would say that's a cosine of the angle. And again, that's equal to our circular acceleration times mass. So here we have that the force of tension is equal to that mv squared over r, that circular acceleration, oops, that should be minus the component of your weight that's pointing towards the center of the circle. So here, when you're at an angle above the center, then the force of tension is less. So force of tension less when we're above the center. If we were below the center, then the force of gravity would be pointing outwards. So if we're below center, then the force of tension would be greater by some factor of your weight. Now, what about if we get to the top of our circle? So if we're at the top and we draw our free body diagram, right, we have the weight, our force of gravity down, and we have our force of tension, oops, where am I drawing that? And we have our force of tension down. Force of tension. They're both pointing in the same direction. Center force points towards the center of the circle. So when I'm at the top, my equation would look like this. Force of tension plus the force of gravity, because they're pointing towards the center of the circle, so plus mg is equal to mv squared over r. So that means that my force of tension is the difference between that circular acceleration times mass and my weight, or the weight of the object. So here we have the minimum force. So you never have to worry about that tension if you're swinging something on a string breaking at the top. If it breaks anywhere, it breaks at the bottom. And of course, we keep going around, right? When I get back to the side, the force of gravity is straight down, the tension force is towards the center of the circle. So I'm back here at the side where the tension force is equal to mv squared over r. So as I move around a circle, the magnitude of my force that's keeping me in the circle changes. At the bottom, it's the greatest. At the top, it's the lightest. And it varies. So as I start at the bottom and I go up, I'm starting at a maximum and it decreases till it's just the tension force is mv squared over r. And then it decreases as I get to the top where I get to my minimum force. So in a vertical circle, it's really hard to maintain uniform circular motion. Because this change in forces, it's very, very difficult to keep something at a constant speed. Please make sure you remember that the acceleration is always positive because it's pointing towards the center of the circle. Now, I like to talk about this thing called losing the loop. And this applies whether we're inside a loop or going over a hill. When you're at the top of a loop in a loop-to-loop, right? Here you are in your roller coaster, right? And your weight points towards the center of the circle because it always points straight down, right? The force of gravity always points straight down. And now this other force on you is a normal force, right? You're sitting in a car, which is sitting on a track, so it's sitting on a surface. So when you're at the top of a loop, you have two forces acting on you. You have your normal force and you have the weight that are keeping you in this circle. So if we go back to that equation that I wrote for the tension force, we're just going to substitute in normal force. Now remember, sometimes I said that sometimes we call the normal force your apparent weight. It's like apparently how you feel, like we talked about it in terms of being in an elevator. Well, if we look at this, right, our normal force is equal to that circular force, that mass times that circular acceleration minus the weight. Now, this is really important. You feel lighter, right? If you think about being in a roller coaster and going around a loop-to-loop, at the bottom you feel real heavy. You feel like they're squishing you into your seat. And at the top you feel lighter. Now, if ever your weight exceeds, if it exceeds that, right, then you're negative and then you're losing the loop, right? You're gone. See ya, bye-bye. That would be bad, right? But there is a critical speed where the only force that keeps you in this loop is your weight. So there is a speed at which your normal force goes to 0. And if you think about that, right, if this were to be 0 and we rearranged for speed, right, weight is mg, that's equal to mv squared over r. We rearrange this, right? The mass is going to go away, and we're going to get the square root of the acceleration due to gravity times r. Now notice it doesn't matter. So when you're in a roller coaster, they don't care how much you weigh to keep you in a circle, because fortunately, as long as there's no friction, which of course there is, so man, that's a whole nother problem, there is a critical speed that keeps you from falling off the track. So when the critical speed is the square root of the radius times g, you're good to go. Now, the bigger the radius is, the faster you can go. But this occurs when it's just the weight that is keeping you in the circle. So guess what you feel? If you can achieve this, which is a scary thing to do, right? Because if there's friction, oh my gosh, then that speed's not the same. But you will feel weightless. So that's really, I can see me now, so I can't write very well. So weightless, when you are at this experience, you're weightless. It's kind of like the same thing if you're driving a car and you go over a hill, if it's a real sharp radius hill, and you're going fast enough, you kind of feel like your stomach is coming up into your mouth, and it's because you have this weightless feeling because you're at this critical speed. You go faster than that and you jump off the road. That's not good. But if you are at speeds less than this critical speed, then this term becomes negative. And if that happens, well, then you lose the loop. That's what we call losing the loop. That would not be good. And then you're in free fall. So you're a parabola. You're going to the ground. So that's why they also put little hooks to keep your wheels on the track, just in case something happens in the car, goes less than the critical speed. But if you can achieve the critical speed, you feel weightless. It is the coolest feeling. Scary. Screaming scary, but pretty awesome. Now, in class, we're going to work this problem together, but I want you to try. It's on the next page. So after you do your WSQ and you submit your question and your answers to the learning check question, I want you to go to the next page and try this. I have a bucket with a mass of 2 kilograms rolled in a vertical circle of radius 1.1 meter. At the lowest point of motion, the tension in the rope is 25 newtons. I want you to find how fast that bucket is going at the bottom. So go back to the equations that we wrote together in the very beginning and see if you can solve this. There's your forces. And then part B is how fast must the bucket move at the top so that the rope doesn't go slack. So what is the critical speed of the bucket? So how the rope wouldn't go slack when the weight is keeping me, or the force of gravity is keeping me in the circle, right? When that tension force is equal to 0. So what is that? Find the speed. So try those, and when you come to class, we'll see how well you did. I'll see you in class.